There is a star in the night sky that has haunted astronomers for nearly 2 centuries. It is not a distant quasar at the edge of the observable universe. It is not a pulsing neutron star buried deep within the spiral arms of a far-off galaxy. It is not some exotic object detected only by satellites and radio dishes. It is the brightest star visible from Earth. You can see it with your own eyes on any clear winter night. It hangs just 8.6 light-years away, so close by cosmic standards that it may as well be sitting on the front porch of our solar system. Its name is Sirius, and it burns with a blue-white brilliance that has guided sailors across oceans, inspired mythologies across continents, and marked the flooding of the Nile for thousands of years. The ancient Egyptians built their entire calendar around its annual rising. The Greeks named the hottest days of summer after it. The Romans sacrificed to it. Polynesian navigators trusted their lives to its position as they crossed thousands of miles of open Pacific. For as long as humans have looked up, Sirius has been there, steady and unblinking, a beacon burned into the collective memory of our species. But Sirius holds a secret. Tucked against its glare, orbiting in a slow gravitational waltz that takes roughly 50 years to complete, there is a second object. Something small, something impossibly dense, something that, when it was first discovered, defied every known principle of physics and forced scientists to rethink the very nature of matter itself. That object is called Sirius B. It is a white dwarf, the collapsed remnant of a star that was once far larger and far more luminous than the companion it now orbits. And within its fading glow lies one of the strangest, most revealing, and most unsettling stories in all of astrophysics. Consider this for a moment. Sirius B is roughly the size of Earth. Its diameter stretches about 12,000 kilometers, comparable to the planet beneath your feet right now. You could drive across it in a matter of hours, theoretically, if there were a road and if you could survive. But Sirius B has a mass approximately equal to that of our Sun, one full solar mass, the entire weight of a star packed into a volume no larger than a modest rocky world. A single teaspoon of its material would weigh roughly 5.5 tons on Earth, not kilograms, tons. If you could scoop out a sugar cube-sized portion of this material and set it on the surface of our planet, it would not sit on a table. It would crash through the table, through the floor, through the concrete foundation beneath, through the bedrock underneath that, and keep falling. The density is not merely extreme. It represents a form of matter that does not exist anywhere on Earth, a form of matter held together not by the bonds of chemistry, not by the electromagnetic forces that govern every object we can touch and see in daily life, but by a quantum mechanical principle so strange and so fundamental that even the brilliant physicists who first proposed it struggled to believe their own equations. And it gets stranger still, because when Sirius B was first predicted, before anyone had ever glimpsed it through a telescope, it was predicted not by studying light or spectra or electromagnetic radiation of any kind. It was predicted by watching the brightest star in the sky wobble. Sirius A was drifting across the heavens in a way that made no sense, not unless something massive and completely invisible was pulling on it from nearby. Something was hiding in the glare, and when that something was finally spotted, decades later, through the largest telescope lens in the world at that time, it defied every expectation. It was too small, it was too dim, it was far too hot for its feeble luminosity, it was far too dense for any known form of matter. It broke the models. It shattered assumptions that had stood for generations, and it opened a door into a realm of physics that would eventually lead to our understanding of quantum degeneracy, stellar death, the theoretical limits of how tightly matter can be compressed, and some of the most powerful thermonuclear explosions in the known universe. By the end of tonight, you're going to understand what Sirius B really is, how it formed, why its discovery nearly upended an entire century of physics, and what it reveals about the ultimate fate of nearly every star in the universe, including our own Sun. You are going to understand what happens when gravity wins, when nuclear fusion ends, and when a star that once dwarfed our entire solar system collapses into something you could fly around in an airplane. You are going to understand why white dwarfs are not just dead stars, but cosmic time capsules, ticking clocks, and, under the right circumstances, thermonuclear weapons of almost unimaginable destructive power. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand Sirius B, we first need to understand Sirius itself. And to understand Sirius, we need to truly grasp, just how close this star is in the grand architecture of the cosmos. The observable universe stretches approximately 93 billion light-years across. That is the diameter of the sphere of space from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. Within that sphere, there are an estimated 2 trillion galaxies, each one a vast, swirling collection of stars, gas, dust, and dark matter bound together by gravity into structures spanning thousands to hundreds of thousands of light-years. The numbers are so large that they lose all intuitive meaning. 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe is estimated at roughly 700 sextillion. That is a 7 followed by 23 zeros. Every grain of sand on every beach on Earth, multiplied by 10,000, still falls short of that count. Our own galaxy, the Milky Way, is a barred spiral disk, roughly 100,000 light-years in diameter and about 1,000 light-years thick in the main disk, though the central bulge extends further. It contains somewhere between 100 billion and 400 billion stars, depending on how one counts the faintest red dwarfs at the bottom of the stellar mass scale. The Sun sits about 26,000 light-years from the galactic center, embedded in a minor spur called the Orion Arm, between the larger Sagittarius and Perseus arms. It orbits the galactic center at a speed of roughly 220 kilometers per second. Even at that velocity, which is about 800,000 kilometers per hour, it takes the Sun approximately 230 million years to complete a single orbit. 1 galactic year. The Milky Way has existed for roughly 13.6 billion years, meaning the Sun has completed about 20 orbits since the galaxy formed, 20 trips around, in all of cosmic history. Within this enormous galactic disk, the distances between individual stars are staggeringly large by human standards, yet almost trivially small compared to the galaxy itself. The average distance between stars in the Sun's neighborhood is about 4 to 5 light-years. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers, or 5.88 trillion miles. These are distances that defy everyday intuition. They are too large for human experience to encompass without aids. The nearest star system to Earth is Alpha Centauri, a triple system composed of 2 sun-like stars and a small red dwarf called Proxima Centauri. The system sits approximately 4.37 light-years away. That translates to about 41.3 trillion kilometers, or 25.7 trillion miles. Light, the fastest thing in the universe, traveling at 299,792 kilometers per second, takes more than 4 years to cross that distance. At the speed of a modern commercial jetliner, roughly 900 kilometers per hour, the journey would take about 5.3 million years. At highway driving speed, say 100 kilometers per hour, it would take roughly 47 million years. If you started driving toward Alpha Centauri at the time the dinosaurs went extinct, 66 million years ago, you would still not have arrived. You would be about 70% of the way there. These comparisons reveal the almost absurd emptiness of interstellar space. After Alpha Centauri, the next nearest stars include Barnard's star, a dim red dwarf about 6 light-years away, Wolf 359, another red dwarf at roughly 7.9 light-years, and Lalande 21,185 at about 8.3 light-years. And then, just slightly farther, we find Sirius, the alpha star of the constellation Canis Major, the Great Dog. Sirius sits 8.6 light-years from Earth. That is roughly 81.4 trillion kilometers, or 50.6 trillion miles, an unimaginable distance by any terrestrial measure. But in a galaxy 100,000 light-years across, 8.6 light-years is almost nothing. Here is a way to truly feel this proximity. If you shrank the entire Milky Way galaxy down to the size of the continental United States, about 4,800 kilometers from New York to Los Angeles, then the distance from the Sun to Sirius would be roughly the length of a single American football field, about 100 meters. We would not be in different states. We would not be in different cities. We would not even be in different neighborhoods. We would be standing on the same block, practically within shouting distance. That is how close Sirius is, by galactic standards. Here is another scaled comparison. If you shrank the Milky Way down to the size of a dinner plate, about 25 centimeters in diameter, the Sun and Sirius would be two specks of dust, so close together that you could cover both with the tip of a ballpoint pen. The entire local stellar neighborhood, all the stars within 20 light-years of the Sun, would fit within a region smaller than a pinhead on that dinner plate. We live in a very small corner of a very large galaxy. This extreme proximity is one of the main reasons Sirius appears so brilliant in our sky. It is not the most inherently luminous star in the galaxy, not even close. There are stars that would make Sirius look like a flashlight next to a stadium spotlight. Rigel, the blue supergiant in the constellation Orion, emits roughly 120,000 times the luminosity of the Sun. Deneb, the supergiant anchoring the Northern Cross in the constellation Cygnus, pumps out nearly 200,000 solar luminosities. Eta Carinae, a massive, unstable star in the southern sky, radiates at roughly 5 million times the luminosity of the Sun. Sirius, by contrast, emits about 25.4 times the Sun's luminosity. It is bright, certainly brighter than average, but it is not a stellar powerhouse by any stretch. The difference is distance. Rigel's is approximately 860 light-years away. Deneb is roughly 2,500 light-years distant. Eta Carinae sits about 7,500 light-years from Earth. Sirius is 8.6 light-years away, and apparent brightness falls off with the square of the distance. A star twice as far away appears 4 times dimmer. A star 10 times farther appears 100 times dimmer. A star 100 times farther appears 10,000 times dimmer. Because Sirius is so staggeringly close, it outshines vastly more luminous stars. It has an apparent magnitude of -1.46, making it the single brightest star in the entire night sky. Only the Sun, the Moon, and occasionally the planets Venus, Jupiter, and Mars outshine it from our vantage point on Earth. Humans have observed Sirius for as long as humans have observed anything in the sky. The ancient Egyptians called it Sopdet. They organized their entire civil calendar around its heliacal rising, the moment each year when Sirius first became visible in the east just before dawn, after a period of roughly 70 days, during which it was hidden below the horizon or lost in the sun's glare. That moment coincided, with remarkable reliability, with the annual flooding of the Nile River. The floodwaters deposited a layer of rich, fertile silt across the floodplain, renewing the soil for the next season's crops. Without the Nile's flood, there was no agriculture. Without agriculture, there was no civilization. The star that announced the flood, the star that told the farmers when to prepare their fields, was Sirius. For the ancient Egyptians, it was not merely a point of light. It was a god, a herald, a cosmic clock upon which the survival of a civilization depended. The Greeks associated Sirius with extreme heat. They believed that its rising, coinciding with the hottest part of summer, actually contributed to the oppressive warmth. They called this period the Dog Days, named after the dog star, and Hippocrates, the father of Medis, warned that the dog days were a time of heightened disease and bodily danger. The Romans performed sacrifices and rituals to appease Sirius. In the traditional astronomy of China, Sirius was the star of the celestial wolf. The Maori of New Zealand used it to mark the onset of winter. Aboriginal Australians incorporated Sirius into their Dreamtime narratives. Polynesian navigators used it as one of their primary reference stars for crossing the Pacific, an ocean spanning more than 15,000 kilometers. In culture after culture, century after century, Sirius occupied a place of exceptional importance. And yet, for all of that attention, for all those thousands of years of watching and recording and worshipping, no one suspected that Sirius was anything other than a single star until the 1800s. The discovery of Sirius B begins with a German astronomer named Friedrich Wilhelm Bessel. Born in 1784 in the town of Minden, Bessel was a largely self-taught mathematician and astronomer who rose to become one of the most precise observational scientists of his era. He was famous for his meticulous attention to error analysis. He catalogued the positions of thousands of stars, calibrated his instruments obsessively, and in 1838 became the first person to measure the parallax of a star, 61 Cygni, thereby providing the first direct measurement of a stellar distance. When Bessel published a number, the astronomical community trusted it. In 1834, Bessel began tracking the proper motion of Sirius. Proper motion is the apparent movement of a star across the sky relative to the distant background of other stars, caused by the star's actual velocity through space, combined with the sun's own motion. All nearby stars exhibit proper motion. The closer the star, the more prominent the motion, just as a nearby bird flies across your field of view much faster than a distant airplane, even if the airplane is moving much faster in absolute terms. Sirius has a proper motion of about 1.3 arcseconds per year, large by stellar standards owing to its proximity. But over a decade of careful measurement, Bessel noticed something peculiar. Sirius was not travelling in a straight line. Its path across the sky showed a slow oscillating wobble, a gentle sinusoidal weave superimposed on its linear drift. The wobble had a period of roughly 50 years. Bessel checked and rechecked. He accounted for atmospheric refraction, the bending of starlight by Earth's atmosphere, which can shift apparent positions by small amounts. He corrected for instrumental flexure. He eliminated parallax effects from Earth's own orbit. The wobble remained. It was real and it was undeniable. By 1844, Bessel had enough data to make a public announcement. He declared that Sirius must have an unseen companion, a massive body orbiting it at close range. The companion's gravitational pull was causing the visible star to trace a wavy path. Using the amplitude and period of the wobble, Bessel estimated the companion's mass at roughly 1 solar mass and its orbital period at about 50 years. This was a stunning prediction. Inferring the existence of an invisible object from gravitational effects alone was a technique that had been used just a few years earlier to predict Neptune, but applying it to a stellar companion was unprecedented. Bessel died in 1846 without seeing his prediction confirmed, but the wobble persisted in every subsequent dataset. The companion was there, hiding in plain sight, waiting for a telescope powerful enough to pull it from the glare. The confirmation came on January 31st, 1862. Alvan Graham Clark, the son of renowned optician Alvan Clark, was testing a newly completed 18.5-inch refracting telescope lens, the largest in the world at that time, destined for the Dearborn Observatory in Chicago. To evaluate the optical quality, Clark pointed the instrument at Sirius. A perfect lens would show the star as a clean point surrounded by neat diffraction rings. Any flaws would produce irregularities. Clark looked through the eyepiece, and there, faint but distinct, close to the first diffraction ring of the overwhelmingly bright primary, he saw a tiny separate point of light. It was dim, roughly 10,000 times fainter than Sirius A. It was close, separated by only a few arcseconds, but it was unmistakably real and unmistakably distinct from the primary. The hidden companion had been found. Bessel, from beyond the grave, was vindicated. The new object was designated Sirius B. Its orbital period was confirmed at roughly 50.1 years. Using the observed orbit and Kepler's third law, astronomers calculated the masses of both stars. Sirius A came in at approximately 2.02 solar masses. Sirius B weighed approximately 0.978 solar masses, nearly the mass of the Sun. This was consistent with Bessel's wobble, but something was deeply wrong. A star with the mass of the Sun should be shining with roughly the luminosity of the Sun. Yet Sirius B was about 10,000 times dimmer. It had hidden, for all of human history, in the glare of its brighter companion. Why was it so faint? Astronomers needed to determine its temperature and size to solve the puzzle. That breakthrough came in 1915. Walter Sidney Adams at Mount Wilson Observatory in California managed to capture a spectrum of Sirius B, an extremely difficult observation requiring the separation of the companion's feeble light from the overpowering glare of the primary. Adams's spectrum revealed hydrogen absorption lines characteristic of a very hot star. The surface temperature was approximately 25,000 degrees Celsius, about 4.5 times hotter than the Sun. This result created a paradox that shook the foundations of astronomy. Sirius B was massive, it was very hot, yet it was incredibly dim. The Stefan-Boltzmann law, which relates luminosity to temperature and surface area, left only one possible resolution. Sirius B had to be extraordinarily small. When astronomers worked through the arithmetic, the answer was startling. Sirius B had to be approximately the size of Earth. A star with the mass of the Sun, compressed into a sphere about 12,000 kilometers across. The Sun's diameter is roughly 1.4 million kilometers. Earth's is about 12,742 kilometers. Sirius B squeezes an entire solar mass into a ball, roughly 109 times smaller in diameter. The resulting density is almost beyond comprehension. Each cubic centimeter of Sirius B material weighs roughly 1 metric ton. A teaspoon would weigh about 5.5 tons. A piece the size of a sugar cube would weigh as much as a car. A chunk the size of a softball would weigh as much as the largest cargo ship ever built. Here is a scaled comparison to make this visceral. If the Sun were the size of a standard beach ball, about 60 centimeters in diameter, then Sirius B would be a small marble, roughly 5.5 millimeters across. But that marble would weigh exactly the same as the beach ball. Imagine holding a marble that weighs as much as a beach ball. That is the density ratio we are dealing with. And even this comparison fails to capture the true absurdity, because a real marble and a real beach ball both weigh very little. To feel the full impact, you would need to imagine a marble that weighs as much as 100,000 loaded freight trains. Arthur Eddington, the brilliant British astrophysicist, captured the mood of the astronomical community when he declared, in 1920, that there was an apparent absurdity in the observations of Sirius B. The density implied by the data was so extreme that Eddington himself struggled to accept it. He remarked that a star should not be allowed to behave in such a fashion. Classical physics offered no mechanism for compressing matter to 1,000,000 grams per cubic centimeter. The atoms should resist. The electrons should push back. Something was fundamentally wrong with the models, or something was fundamentally new about the physics. That something was quantum mechanics, and the resolution of the paradox would arrive from an unexpected direction, aboard a steamship crossing the Indian Ocean. The problem with Sirius B was not merely that it was small and dense. The problem was that, according to every principle of physics that had been established up to that point, such an object should have been flat out impossible. Its very existence was a contradiction, and resolving that contradiction required scientists to abandon familiar assumptions about the behavior of matter and venture into a domain of physics that was, in the 1920s, only beginning to take shape. To understand why Sirius B seemed impossible and why its explanation required a revolution, we need to think carefully about what holds a star up. What prevents a ball of gas weighing 2 nonillion kilograms, that is 2 times 10 to the 30 kilograms, from simply collapsing under its own gravitational weight? The answer for a living star is a war, a continuous, violent, billion-year struggle between two titanic forces. On one side is gravity. Gravity is the weakest of the 4 fundamental forces, but it has an advantage that the other forces lack. It is always attractive, it operates over unlimited distances, and it is cumulative. The more mass you pile together, the stronger the pull. Gravity does not negotiate, it does not tire, it is relentless. It pulls every particle of mass toward every other particle of mass, and in a star-sized object, that pull is enormous. If gravity were the only force acting on the Sun, the entire star would collapse to a point in less than 30 minutes, 27 minutes, to be precise. That is how quickly gravity would win if nothing opposed it. On the other side is pressure. In a normal active star like the Sun, the outward pressure comes from nuclear fusion. Deep in the core, at temperatures of roughly 15 million degrees Celsius and pressures exceeding 250 billion atmospheres, hydrogen nuclei are forced together with enough violence to overcome their mutual electromagnetic repulsion. They fuse. 4 hydrogen nuclei combine through a series of intermediate steps to form one helium nucleus. The helium nucleus weighs very slightly less than the 4 hydrogen nuclei that created it. The missing mass, about 0.7% of the original, is converted into energy according to Einstein's relation between energy and mass. That energy manifests as gamma-ray photons and kinetic energy of the particles involved. The photons bounce and scatter their way outward through the star, taking hundreds of thousands of years to travel from the core to the surface, losing energy at each interaction, degrading from gamma rays to X-rays to ultraviolet to visible light. Along the way, they heat the stellar material, maintain its temperature, and sustain the thermal pressure that pushes outward against gravity. This balance is called hydrostatic equilibrium, and it is elegantly self-correcting. If the core contracts slightly, the increased density and temperature boost the fusion rate, generating more energy, increasing the pressure, and pushing the core back outward. If the core expands slightly, the lower density and temperature reduce the fusion rate, decreasing the pressure and allowing gravity to pull the core back inward. The star oscillates gently around its equilibrium point, maintaining a stable size and luminosity for billions of years. Our Sun has been in this balanced state for roughly 4.6 billion years, and will remain so for approximately another 5 billion. But this equilibrium rests on a finite resource. The Sun converts roughly 620 million metric tons of hydrogen into helium every second. 620 million tons every second. That sounds catastrophic, but the Sun is so enormous, roughly 2 times 10 to the 30 kilograms, that it contains enough hydrogen to sustain this rate for roughly 10 billion years in total. We are currently about halfway through the budget. When the hydrogen in the core is consumed, the equilibrium collapses. The core, now a ball of inert helium ash, generates no energy. Without energy, there is no thermal pressure. Without thermal pressure, gravity takes over. The core begins to contract. As it contracts, it heats up, because gravitational compression converts gravitational potential energy into thermal energy. The layers of hydrogen just above the core, heated by this contraction, begin fusing in a thin shell around the dead helium center. This shell burning is inherently unstable. It generates tremendous energy, more than the star can comfortably radiate from its existing surface area. The outer layers of the star respond by ballooning outward, expanding to enormous size. The surface cools as it stretches, shifting from yellow or white to orange, and eventually red. The star becomes a red giant. If the Sun were to become a red giant today, its outer atmosphere would swell to perhaps 100 or 200 times its current diameter. That would engulf Mercury. It would engulf Venus. Earth's fate is uncertain but grim. Even if Earth is not physically swallowed, its surface would be baked to temperatures of thousands of degrees, sterilizing it completely. The oceans would boil away. The atmosphere would be stripped. Everything that ever lived here would be erased. Meanwhile, inside the red giant, the helium core continues to contract and heat. When the core temperature reaches approximately 100 million degrees Celsius, a new set of nuclear reactions ignites. Helium nuclei begin fusing. In the triple alpha process, 3 helium nuclei, each called an alpha particle, collide and combine to form a single carbon nucleus. Some of those carbon nuclei then capture an additional alpha particle to form oxygen. Helium burning is less efficient than hydrogen burning. It produces less energy per reaction and lasts for a much shorter time. For a star of modest mass, this helium burning phase might last 100 million years, perhaps less. For more massive stars, it can be shorter still. For stars below roughly 8 solar masses, which includes the Sun and the progenitor of Sirius B, the sequence essentially ends with carbon and oxygen. The core temperature never rises high enough to fuse carbon, which requires roughly 500 million degrees, or oxygen, which requires even more extreme conditions. The nuclear furnace shuts down for good. The core sits there, composed of carbon and oxygen, generating no energy, producing no outward pressure, held up by nothing more than the thermal energy it accumulated during its contraction. The star sheds its outer layers. Over tens of thousands of years, the bloated envelope of the red giant drifts away into space, pushed by radiation pressure and stellar winds. This expanding shell of gas, illuminated by the ultraviolet radiation of the exposed hot core, glows as a planetary nebula. These objects are among the most photogenic in astronomy. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, sometimes called the Eye of God, the Cat's Eye Nebula in Draco, with its intricate nested shells, the Dumble Nebula in Vulpecula. All of them are the shed skins of dying stars, beautiful in their own right, but each one a testament to a death. And left behind at the centre, stripped of its garments, is the core, a ball of carbon and oxygen, roughly the mass of the Sun, in some cases more, in others less, compressed by gravity to a size comparable to Earth. This is a white dwarf. This is what Sirius B is. Now we reach the fundamental question that haunted physicists for decades. What holds the white dwarf up? The white dwarf has no fusion, no nuclear reactions, no energy generation of any kind. Classical thermodynamics says that pressure depends on temperature, and a white dwarf is cooling. It is radiating its stored heat into space, slowly but inexorably. As it cools, its thermal pressure should decrease. As the pressure drops, gravity should tighten its grip. The white dwarf should shrink. It should continue shrinking as it continues cooling, contracting without limit toward infinite density. But this is manifestly not happening. White dwarfs exist. They are stable. They maintain their sizes for billions of years, even as they cool dramatically. Something is holding them up. Something that does not depend on temperature. Something that classical physics cannot explain. The resolution came from quantum mechanics, the strange and counterintuitive framework of physics that governs the behavior of matter at atomic and subatomic scales. Specifically, the answer involves the Pauli exclusion principle, formulated by the Austrian physicist Wolfgang Pauli in 1925. The principle states, with absolute finality, that no two identical fermions can occupy the same quantum state at the same time. Fermions are particles with half-integer spin, and they include electrons, protons, and neutrons, the building blocks of all ordinary matter. Two electrons in the same system cannot have exactly the same set of quantum numbers, the same energy level, the same angular momentum, the same spin orientation. If the lowest states are full, the next electron must go higher. There is no exception. This is not a tendency or a preference. It is an ironclad law of nature, as fundamental as conservation of energy, or the constancy of the speed of light. Under ordinary conditions, at the densities we experience in daily life, the Pauli exclusion principle operates quietly in the background. It explains why the periodic table looks the way it does, why electron orbitals fill in the order they do, why matter is solid rather than collapsing into a dense blob. But it is not the dominant force determining the behavior of materials. At everyday densities, there is plenty of quantum mechanical room. The electrons are spread out. The exclusion principle is easily satisfied. Inside a white dwarf, the situation is radically different. The density is roughly 1 million grams per cubic centimeter. For comparison, water is 1 gram per cubic centimeter. Granite is about 2.7. Iron is about 7.9. The densest naturally occurring element on Earth, osmium, has a density of roughly 22.6 grams per cubic centimeter. White dwarf material is roughly 44,000 times denser than osmium. It is roughly 130,000 times denser than iron. There is nothing in human experience, nothing you have ever touched, seen, or interacted with, that comes remotely close to this density. At such extreme compression, the atoms no longer exist as atoms. They are fully ionized. Every electron has been stripped from every nucleus. The bare nuclei, carbon and oxygen cores without any electron clouds, form a dense lattice or fluid, and the electrons, liberated from their atomic homes, swarm freely through the material, forming a vast, dense, quantum mechanical sea. It is this electron sea that saves the white dwarf from collapse. The electrons are packed so tightly that the lowest available quantum states are completely occupied. Every energy level, from the lowest possible upward, is full. There is literally no room for any electron to move to a lower state. They are jammed together in quantum state space as tightly as the laws of physics permit. And this extreme crowding generates a pressure, a quantum mechanical pressure, that resists further compression. This pressure is called electron degeneracy pressure. It is different from any force in classical physics. It does not depend on temperature. It depends only on density. Cool the white dwarf to absolute zero, and the pressure remains. The electrons simply cannot be squeezed any further. They have filled every available state, and the Pauli exclusion principle forbids them from sharing. The white dwarf is held up not by heat, not by fusion, not by any process that generates energy, but by the quantum mechanical identity of electrons, by their refusal, written into the deepest structure of reality, to occupy the same state as their neighbours. This is what holds Sirius B up. This is the force that prevents it from collapsing further. The entire star, a ball of matter as massive as the Sun, is balanced on a principle of quantum mechanics that was not even discovered until 1925. For thousands of years, humans watched Sirius burn in the sky, never suspecting that beside it hung an object whose very existence depended on physics that had not yet been imagined. Eddington, upon hearing this explanation, expressed deep unease. He felt there ought to be a law of nature to prevent a star from behaving so absurdly. The idea that matter could exist at 1,000,000 grams per cubic centimetre, held up by a quantum statistical effect, struck him as almost indecent, but he was wrong to protest. Nature owed him no apologies. The mathematics was rigorous. The predictions matched the observations. Sirius B existed exactly as the new quantum theory described, and it gets worse, because the quantum mechanical safety net has a limit. And the physicist who discovered that limit was barely 20 years old. In 1930, Subrahmanyan Chandrasekhar, born in Lahore in 1910 and educated in Madras, was travelling by steamship from India to Cambridge, England, where he had been awarded a fellowship. The voyage took several weeks, and Chandrasekhar, a prodigious young theorist, used the time to work on a problem that fascinated him. He wanted to know what happened to a white dwarf as it gained mass. Specifically, he wanted to combine the principles of Einstein's special relativity with the theory of electron degeneracy pressure and work out the structure of the most massive possible white dwarf. The calculation was elegant and its result was devastating. As a white dwarf becomes more massive, its core becomes denser. As the density rises, the electrons are forced into higher and higher energy states by the exclusion principle. Higher energy states correspond to higher velocities. At a certain critical mass, the electrons in the core are forced to speeds approaching the speed of light. They become relativistic. And relativistic electrons, Chandrasekhar found, provide less pressure per unit of energy than their slower counterparts. The equation of state, the relationship between pressure and density, softens. Gravity, which grows steadily stronger with increasing mass, begins to outpace the degeneracy pressure, which grows more slowly at relativistic speeds. The result is a maximum mass, a ceiling, a hard limit written into the structure of the universe by the constants of nature. That limit is approximately 1.4 solar masses. Below this limit, electron degeneracy pressure wins. The white dwarf is stable. It will endure for trillions of years, cooling slowly but never collapsing. Above this limit, gravity wins. The electrons cannot hold. The white dwarf must collapse. The electrons are forced into the protons, forming neutrons through inverse beta decay, and the star compresses to a neutron star, a sphere perhaps 20 kilometers across, with a density of roughly 1,000,000,000 tons per cubic centimeter. If even neutron degeneracy pressure is exceeded, the collapse continues to a black hole. This limit is now called the Chandrasekhar limit. It is one of the most important numbers in astrophysics, and Sirius B sits just below it, at approximately 0.978 solar masses. A margin of about 0.42 solar masses separates this ancient white dwarf from catastrophe. The electrons are holding. The quantum pressure is winning the war, but the margin is finite, and in a binary system where mass can flow between companions, finite margins can be erased. The surface gravity of Sirius B is roughly 350,000 times that of Earth. If you somehow stood on its surface, you would weigh about 25 million kilograms. A single paperclip would weigh as much as a small car. The escape velocity is about 5,100 kilometers per second, nearly 2% of light speed. Compared to Earth's escape velocity of 11.2 kilometers per second, Sirius B's gravitational grip is staggering. Light climbing away from the surface of Sirius B loses energy. It is redshifted, stretched to longer wavelengths by the effort of escaping the gravitational well. This gravitational redshift predicted by Einstein's general theory of relativity, was measured by Walter Adams in 1925 and found to match the theoretical predictions beautifully. It was one of the earliest confirmations of general relativity and proved that the space-time around Sirius B is measurably warped. The white dwarf is not just dense, it is a literal dent in the fabric of the universe. The surface temperature of Sirius B currently hovers at about 25,200 degrees Kelvin, far hotter than the Sun's 5,800 degree surface. But this heat is inherited, not generated. No reactions are producing energy inside Sirius B. It is simply radiating away the thermal energy stored during its formation. Over hundreds of millions of years it will cool. Over billions of years it will dim. Over tens of billions of years it will fade from white to yellow to red. And over timescales far exceeding the current age of the universe, perhaps 100 trillion years, it will cool to near absolute zero, becoming a hypothetical object called a black dwarf, a cold, dark, invisible sphere of crystallized carbon and oxygen, drifting through an equally dark and empty universe. No black dwarf has yet formed anywhere in the cosmos. The universe is simply too young. The oldest white dwarfs still glow faintly, patient beyond all human measure. This patience makes them extraordinary tools for astronomy. White dwarfs cool at predictable rates determined by their mass, composition, and initial temperature. By measuring a white dwarf's current temperature, astronomers can estimate when it formed. The coolest, faintest white dwarfs in any stellar population set a lower limit on that population's age. This technique has been used to estimate the age of the Milky Way's disk at roughly 8 to 9 billion years, and the galactic halo at 11 to 12 billion years. White dwarfs keep time for the galaxy itself. Sirius B formed roughly 120 million years ago, when its progenitor, a main sequence star of approximately 5 solar masses, exhausted its fuel. That star lived fast. Stars 5 times the mass of the Sun burn through their hydrogen in roughly 100 million years, compared to the Sun's 10 billion year lifespan. Massive stars are profligate with their fuel. The higher their mass, the hotter their cores, the faster they fuse, and the sooner they die. A 10 solar mass star lives about 20 million years. A 50 solar mass star might survive only 3 or 4 million years. But a star half the Sun's mass can burn for well over 20 billion years, far longer than the current age of the universe. In the cosmic economy, the spendthrifts die first, and the misers inherit everything. The progenitor of Sirius B was once the dominant member of the binary system. It was more massive than Sirius A. It was more luminous. It was the star any ancient observer would have noticed first. But it exhausted its fuel, swelled into a red giant, shed its outer atmosphere, and collapsed into the dim remnant we observe today. The king became the pauper, the bright one dimmed, the great one shrank, and the lesser companion, Sirius A, carries on, shining steadily, still burning hydrogen, still young by stellar standards. But here's what makes this truly terrifying. Sirius A will not burn forever either. In roughly 600 into a billion years, it too will begin to exhaust its hydrogen. It will swell into a red giant. Its outer layers will expand enormously, and as they expand, they may reach across the space between the two stars and begin falling onto the surface of Sirius B. Mass will flow from the living star to the dead one, and if enough mass accumulates, if the white dwarf approaches 1.4 solar masses, the quantum mechanical safety net will fail. The consequences of that failure are among the most violent events the universe is capable of producing. But before we reach that cataclysm, we must appreciate just how difficult Sirius B has been to study. Because knowing that something exists and actually observing it in meaningful detail are two vastly different achievements, separated by decades of frustration, ingenuity, and the relentless refinement of instruments and methods. The fundamental problem is glare. Sirius A is roughly 10,000 times brighter than Sirius B. Imagine standing in a darkened field, trying to photograph a candle flame placed 3 feet from a lighthouse. The lighthouse overwhelms everything. Its light floods your detector, scatters through your optics, bleeds across every pixel. The candle is there, you know it is there, but the lighthouse will not allow you to see it clearly. That is the challenge of observing Sirius B from the ground. The atmosphere of the Earth makes things worse. Turbulence in the air smears starlight into flickering blobs. On a night of average seeing, the image of Sirius A spreads into a disk perhaps 2 arcseconds wide, and the scattered light from that disk reaches right out to the position of Sirius B, drowning it in a luminous haze. Ground-based telescopes struggled with this for over a century. Observers could confirm Sirius B's existence through its gravitational effects and catch occasional glimpses through large telescopes under exceptionally steady atmospheric conditions, but obtaining detailed, precise measurements of its properties was a grinding battle against the physics of light and air. The earliest spectroscopic measurements, like those of Walter Adams in 1915 and again in 1925, were heroic achievements performed at the limits of the technology of the day. Adams used the 60-inch and 100-inch reflectors at Mount Wilson Observatory, among the most powerful telescopes on Earth at the time, and even with these instruments, separating Sirius B's faint light from the overwhelming glare of Sirius A required extraordinary skill, patience, and favorable atmospheric conditions. There was also the problem of contamination. When you are trying to measure the spectrum of a faint star sitting next to a brilliant one, some light from the bright star inevitably leaks into your spectrograph. This scattered light contaminates the spectrum, making it appear as though the faint star has features it does not actually possess, or masking features that it does. Adams's early measurements of the gravitational redshift of Sirius B were called into question for decades, partly because of concerns about scattered light from Sirius A. Did the measured redshift truly belong to the white dwarf, or was it an artifact of contamination? The debate simmered through the middle decades of the 20th century, casting a faint but persistent shadow of doubt over one of general relativity's early triumphs. The solution, when it finally came, arrived from orbit. In 1990, the Hubble Space Telescope was launched into low Earth orbit, and although its primary mirror suffered from a well-publicized flaw in its curvature, corrective optics installed during a servicing mission in 1993 transformed it into the sharpest optical telescope ever deployed. Above the atmosphere, free from turbulence and scattering, Hubble could resolve details that no ground-based instrument could match. And in 2004 and 2005, a team led by Martin Barstow at the University of Leicester pointed Hubble at the Sirius system to perform the most precise measurement of Sirius B's gravitational redshift ever attempted. The results, published in 2005, were remarkable. Barstow and his colleagues used the Space Telescope Imaging Spectrograph, an instrument capable of isolating the light of Sirius B with unprecedented precision, to measure the redshift of the hydrogen Balmer lines in the white dwarf's atmosphere. The measurement agreed with the prediction of general relativity to within a few percent. The gravitational redshift corresponded to a mass of 0.978 solar masses, consistent with independent dynamical mass measurements. The ghost of doubt that had haunted Adams's early measurements was finally laid to rest. Einstein was right. The space-time around Sirius B was warped precisely as the equations predicted, and the scattered light concerns that had plagued ground-based spectroscopy for 70 years were overcome by the simple expedient of placing the telescope above the offending atmosphere. But Hubble's contribution went further. Its sharp imaging also allowed astronomers to refine the orbital parameters of the Sirius binary system with extraordinary accuracy. The orbit of Sirius B around Sirius A, or more precisely, both stars around their common center of mass, has a period of approximately 50.09 years, an eccentricity of about 0.59, and a semi-major axis of roughly 7 astronomical units. At closest approach, periapsis, the two stars are separated by about 8 astronomical units, roughly the distance from the Sun to Saturn. At their widest separation, apopsis, they are about 31.5 astronomical units apart, comparable to the distance from the Sun to Neptune. These distances are enormous by terrestrial standards, but remarkably small by stellar standards, making the Sirius system a tight and dynamically interesting binary. The refinement of the orbit matters because it constrains the mass of both stars. By applying Kepler's third law and Newton's law of gravitation, The orbital period and semi-major axis directly yield the total mass of the system, and combined with the observed motion of each star around the center of mass, the individual masses can be determined. The mass of Sirius A is approximately 2.06 solar masses. The mass of Sirius B is approximately 0.978 solar masses. These numbers are known with remarkable precision, and they tell a story. The numbers are striking when you convert them to human terms. The total mass of the Sirius system is about 3 solar masses, or roughly 6,000 billion kilograms. This immense quantity of matter is divided between two objects separated by a distance that varies between roughly 1.2 billion and 4.7 billion kilometers, completing one orbit in the time it takes a human to go from birth to retirement. If you shrank the Sirius system so that the semi-major axis of the orbit equaled 1 meter, Sirius A would be a sphere about 0.2 of a millimeter across, a grain of fine sand, and Sirius B would be an almost invisible mote, roughly 1/100th of a millimeter in diameter, smaller than a human red blood cell. Yet that tiny mote would weigh the same as the grain of sand. This mismatch between size and mass is what makes Sirius B so physically extraordinary. The observation of Sirius B has also benefited from advances in adaptive optics, a technology that corrects for atmospheric turbulence in real time. Ground-based telescopes equipped with adaptive optics systems use deformable mirrors that flex hundreds of times per second, counteracting the shimmering and blurring caused by pockets of air at different temperatures moving across the line of sight. By cancelling the distortions introduced by the atmosphere, adaptive optics can produce images almost as sharp as those from space telescopes. Several teams have used adaptive optics on large ground-based telescopes, including the Very Large Telescope in Chile and the Keck telescopes in Hawaii, to image Sirius B independently of Hubble. These observations have provided complementary data on the white dwarf's position, brightness, and color, helping to cross-check and refine the measurements made from orbit. Infrared observations have added yet another dimension to our understanding of Sirius B. At infrared wavelengths, the brightness contrast between Sirius A and Sirius B is less extreme than in visible light, because the white dwarf's high surface temperature means it emits a larger fraction of its radiation at shorter wavelengths, while the cooler Sirius A is relatively brighter in the infrared. This reduced contrast makes it somewhat easier to detect the white dwarf at longer wavelengths, and infrared photometry has been used to constrain the temperature and radius of Sirius B, independently of optical measurements. The consistency between optical, ultraviolet, and infrared data provides confidence that our models of the white dwarf's atmosphere and thermal structure are fundamentally sound. X-ray observations tell a different part of the story. Sirius B has been detected as an X-ray source by several space observatories, including Rossat and the Chandra X-ray Observatory. The X-ray emission is soft, meaning it consists primarily of low-energy X-ray photons, consistent with thermal radiation from the hot surface of the white dwarf. The detection confirms the high surface temperature independently of optical spectroscopy and allows astronomers to probe the uppermost layers of the atmosphere, where temperatures are highest, and the physics of the atmospheric boundary transitions from degenerate to non-degenerate matter. The mass of Sirius B tells us that its progenitor must have lost a tremendous amount of material during its death. The progenitor began life with roughly 5 solar masses. The white dwarf remnant retains less than 1. Where did the rest go? It was expelled into space during the asymptotic giant branch phase, when the dying star pulsed and shuddered, its outer layers driven outward by radiation pressure, thermal pulses, and powerful stellar winds. These expelled layers formed a planetary nebula, a glowing shell of ionized gas surrounding the newly exposed core. The planetary nebula of Sirius B's progenitor has long since dispersed and faded. Planetary nebulae are transient phenomena, lasting only 20,000 to 50,000 years before they dissipate into the interstellar medium. The event happened roughly 120 million years ago, so the nebula dissolved over 100 million years before the first dinosaurs walked the Earth. There is no trace of it left. Only the white dwarf remains, a crystallized memory of a star that once blazed 5 times brighter than our own sun. The composition of Sirius B carries information about the nuclear processes that forged it. Spectroscopic analysis reveals that its atmosphere is composed almost entirely of hydrogen. This classifies it as a Da-type white dwarf, the most common variety. The hydrogen forms a thin veneer, perhaps only 100 kilometers thick, floating atop a layer of helium, which in turn sits above the carbon-oxygen core. The stratification occurs because of the intense surface gravity. In a gravitational field 350,000 times stronger than Earth's, heavier elements sink rapidly to the bottom, and lighter elements float to the top. The atmosphere is gravitationally sorted with ruthless efficiency. Any heavy elements that might drift onto the surface from the interstellar medium or from a companion star's wind quickly sink out of sight, leaving only the lightest element, hydrogen, at the top. This gravitational settling is so effective that it creates an observational puzzle. We know the core must be rich in carbon and oxygen, the products of helium fusion in the progenitor star's final burning phases. We know there must be an intermediate layer of helium, but we cannot see any of this from outside. All we see is hydrogen. The white dwarf hides its internal composition behind a mask of gravitational purity. Determining what lies beneath requires theoretical models of white dwarf structure, validated against observations of pulsating white dwarfs, whose oscillations probe their interiors, much as earthquakes reveal the structure of the Earth. The study of white dwarf interiors through pulsations is called asteroseismology, and it has revealed extraordinary things. Some white dwarfs pulsate in complex patterns of non-radial oscillations, their surfaces rising and falling in tessellated waves, driven by opacity-related instabilities in their outer layers. By measuring the frequencies of these oscillations, astronomers can construct models of the star's internal density profile, temperature gradient, and chemical stratification. Sirius B itself is not a known pulsator. Its surface temperature places it outside the instability strips, where pulsations are typically observed, but the techniques developed from studying other pulsating white dwarfs inform our understanding of its likely internal structure. And then there is the matter of crystallization. In 1960, physicist Hugh Van Horn predicted that as a white dwarf cools, its carbon-oxygen core will eventually undergo a phase transition from liquid to solid. The ions in the core, carbon and oxygen nuclei stripped of their electrons, will arrange themselves into a regular lattice structure. The white dwarf will crystallize. It will become, in essence, a giant diamond, or more precisely, a giant crystal of carbon and oxygen, with a lattice structure determined by the electrostatic interactions between the ions and the pressure of the surrounding degenerate electron gas. For decades, this prediction remained theoretical. Then, in 2019, a team led by Pierre-Emmanuel Tremblay at the University of Warwick used data from the European Space Agency's Gaia spacecraft to identify a clear observational signature of crystallization in white dwarfs. Gaia, which was launched in 2013 to map the positions and motions of over 1 billion stars in the Milky Way, with unprecedented precision, provided accurate distances and hence luminosities for tens of thousands of white dwarfs. When Tremblay and his colleagues plotted these white dwarfs on a color magnitude diagram, a graph of luminosity versus surface temperature, they found a pileup, an excess of stars at a particular luminosity range. This pileup corresponded exactly to the luminosities and temperatures at which crystallization was predicted to begin. The physics is elegant. When a white dwarf crystallizes, the phase transition releases latent heat, just as water releases heat when it freezes into ice. This extra energy source slows the cooling of the white dwarf, causing it to linger at a particular luminosity longer than it would otherwise. The result is a pileup. More white dwarfs observed at that luminosity than cooling models without crystallization would predict. Tremblay's team found exactly this pileup at exactly the predicted location in a sample of over 15,000 white dwarfs within 300 light-years of the Sun. Crystallization in white dwarfs was no longer a theoretical curiosity. It was an observed reality. Has Sirius B begun to crystallize? Given its mass of about 0.978 solar masses and its current surface temperature of about 25,200 Kelvin, it is likely still too hot for crystallization to have begun in its core. The onset of crystallization depends on mass and temperature, with more massive white dwarfs crystallizing at higher temperatures because their cores are denser. Models suggest that Sirius B may begin to crystallize in a few 100 million to a billion years. When it does, it will join the cosmic majority. Tremblay's analysis suggested that roughly half of all white dwarfs within 100 parsecs of the Sun have already begun to crystallize. Our galaxy is filled with crystallized stellar remnants, ancient hearts of dead stars turned to solid carbon and oxygen, drifting silently through the dark. Now we must turn to the most dramatic role that white dwarfs play in the cosmos, a role that connects Sirius B to the deepest questions in modern cosmology. It involves destruction on a scale that dwarfs even the death of the star that created the white dwarf in the first place. It involves Type Ia supernovae. A Type Ia supernova is one of the most energetic events in the universe. For a few weeks, a single exploding white dwarf can outshine an entire galaxy of 400 billion stars. The explosion releases roughly 10 to the 44 joules of energy, a number so large that it defies meaningful comparison with anything in human experience. The blast destroys the white dwarf completely, leaving no remnant, no neutron star, no black hole, nothing. The entire mass of the star is flung outward at velocities reaching 10,000 to 20,000 kilometers per second, seeding the surrounding space with heavy elements forged in the thermonuclear fury of the explosion. The mechanism at its heart is straightforward. A white dwarf near the Chandrasekhar limit becomes sufficiently hot and dense at its center that carbon fusion ignites. But unlike the controlled, steady fusion that powers a main sequence star, this ignition is catastrophic. A main sequence star can regulate its fusion rate through a thermostat-like feedback loop. If the core gets too hot, it expands slightly, which cools it, which slows the fusion rate. But a white dwarf is supported by electron degeneracy pressure, which does not depend on temperature. If fusion ignites and heats the core, the star does not expand. The temperature rises further. The fusion rate increases. The temperature rises again. The fusion rate increases again. There is no thermostat. There is no regulation. There is only a runaway thermonuclear detonation that incinerates the entire star in a matter of seconds. The details of how the explosion propagates through the white dwarf remain an active area of research. There are two primary scenarios. In the first, the detonation begins at or near the center and propagates outward as a supersonic detonation wave, fusing carbon and oxygen into heavier elements all the way to nickel and iron. In the second, the burning begins as a slower subsonic deflagration, a turbulent flame front that simmers and billows through the star before transitioning to a full detonation at some critical point. The deflagration to detonation transition model is currently favored by many researchers because it produces synthetic light curves and spectra that better match the observations. But the precise physics of the transition remains poorly understood. Three-dimensional simulations of the explosion, performed on some of the world's most powerful supercomputers, are still working to resolve the details. What makes Type Ia supernovae cosmologically important is their uniformity. Because the explosion is triggered at a well-defined mass, the Chandrasekhar limit, the energy released is approximately the same for every Type Ia supernova. This makes them standard candles, objects of known intrinsic brightness that can be used to measure cosmic distances. If you know how bright something truly is, and you measure how bright it appears, the difference tells you how far away it is. This is the same principle by which you estimate the distance to an approaching car at night by the apparent brightness of its headlights. In the late 1990s, two independent teams used Type Ia supernovae as standard candles to measure the distances to galaxies billions of light-years away. The teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rias, expected to find that the expansion of the universe was slowing down, decelerating under the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The universe's expansion was accelerating. The most distant supernovae were fainter than expected, meaning the galaxies hosting them were farther away than a decelerating universe would predict. Something was pushing the universe apart, something that acted against gravity, something that grew stronger as space expanded. That something was dubbed dark energy, and its discovery is one of the most profound in the history of science. Dark energy appears to constitute roughly 68% of the total energy content of the universe. It permeates all of space. Its nature remains almost entirely unknown. It may be the cosmological constant that Einstein introduced and then abandoned, a fixed energy density inherent to the vacuum of spacetime itself. It may be a dynamic field that evolves over time. It may be something entirely unanticipated by current physics. The discovery earned Perlmutter, Schmidt, and Rias the Nobel Prize in Physics in 2011, and it rested on the shoulders of exploding white dwarfs. Sirius B itself is not going to explode as a Type Ia supernova, at least not anytime soon. It is currently well below the Chandrasekhar limit, and Sirius A, while it will eventually expand into a red giant, is unlikely to transfer enough mass to push its companion over the edge in any timescale relevant to human civilization. But Sirius B belongs to the class of objects that makes these explosions possible. It is a white dwarf in a binary system, and binary white dwarfs are the engines of Type Ia supernovae. Every Type Ia that has ever detonated began as something very much like Sirius B, a dead stellar core, inert and patient, sitting beside a companion star from which it could, given the right circumstances, steal enough mass to seal its own destruction. There is, however, an alternative model for Type Ia supernovae that does not require mass transfer from a companion star. This is the double degenerate model, in which two white dwarfs in a close binary system spiral together and merge. As they orbit, they lose energy through the emission of gravitational waves, ripples in the fabric of spacetime predicted by Einstein's general theory of relativity, and detected directly for the first time in 2015 by the LIGO Observatory. The gravitational wave emission causes the orbit to shrink. The white dwarfs spiral closer and closer. Eventually, they merge. If the combined mass exceeds the Chandrasekhar limit, carbon fusion ignites, and the result is the same catastrophic detonation. This model is particularly appealing because it naturally explains why no hydrogen is observed in the spectra of Type Ia supernovae, a prediction that follows directly from the merger of two objects composed of carbon, oxygen, and helium, with only trace amounts of hydrogen. Both models, the single degenerate scenario involving mass transfer from a normal star, and the double degenerate scenario involving the merger of two white dwarfs, likely contribute to the observed population of Type Ia supernovae. The relative importance of each channel is an active area of research, with implications for the use of these explosions as cosmological distance indicators. If different progenitor channels produce supernovae with subtly different peak luminosities, then the assumption of a single, universal standard candle may need to be refined. This potential for systematic error in the standard candle calibration has motivated enormous efforts to understand the diversity of Type Ia supernovae in greater detail. Surveys like the Dark Energy Survey, the Zwicky Transient Facility, and the upcoming Legacy Survey of Space and Time at the Vera C. Rubin Observatory are designed to discover and characterize thousands of Type Ia supernovae per year, building statistical samples large enough to identify and correct for subtle correlations between supernova properties and their progenitor systems. The more precisely we can calibrate the standard candle, the more precisely we can measure the expansion history of the universe, and the tighter the constraints we can place on the nature of dark energy. The physics of white dwarfs, an area of study that might seem esoteric and disconnected from the grand questions of cosmology, turns out to be central to our understanding of the fate of the entire universe. But here's the problem. Despite decades of effort, the progenitor systems of Type Ia supernovae have never been directly observed before the explosion. In a few cases, pre-explosion images of the location of a Type Ia supernova exist, taken by chance during earlier surveys of the same patch of sky. These images have been scrutinized for the presence of a companion star or a luminous accretion disk, but in most cases, nothing is detected above the background noise. This absence of direct detections has been interpreted as evidence favoring the double degenerate model, in which the progenitor is a pair of faint white dwarfs rather than a white dwarf with a bright, easily detectable companion. But the absence of evidence is not evidence of absence, and the debate continues, fueled by each new supernova discovery and each new theoretical model. White dwarfs also produce less dramatic but still spectacular explosions called novae. A nova occurs when a white dwarf in a binary system accretes hydrogen from its companion star. The accreted hydrogen accumulates on the surface of the white dwarf, compressed and heated by the immense gravity. When the temperature and density at the base of the accreted layer reach a critical threshold, hydrogen fusion ignites in a runaway thermonuclear flash. The explosion ejects the accreted material into space at velocities of several thousand kilometers per second, producing a brilliant flare of light that can increase the system's brightness by a factor of 50,000 to 100,000 or more. Unlike a type-A supernova, a nova does not destroy the white dwarf. The underlying star survives, and the cycle can repeat. Some novae are observed to recur on timescales of decades to centuries, earning the designation recurrent novae. The most famous recurrent nova is RS Ophiuchi, a system consisting of a white dwarf near the Chandrasekhar limit and a red giant companion. RS Ophiuchi observed to erupt in 1898, 1933, 1958, 1967, 1985, 2006, and most recently in 2021. Each eruption ejects a shell of material but leaves the white dwarf slightly more massive than before, because not all of the accreted material is expelled. The white dwarf appears to be slowly gaining mass with each cycle, creeping toward the Chandrasekhar limit. Whether it will eventually reach that limit and detonate as a Type Ia supernova remains an open question, one that connects the violent number of novae to the even more violent drama of supernovae across a continuum of stellar death. Could Sirius B undergo nova eruptions? In principle, if mass were to flow from Sirius A to Sirius B, the accreted hydrogen could ignite in thermonuclear flashes, but the conditions are not currently favorable. Sirius A is a main sequence star of modest size, not a swollen giant. The two stars are separated by several astronomical units at closest approach. Mass transfer requires the donor star to fill its Roche lobe, the teardrop-shaped region of space, within which material is gravitationally bound to that star. Sirius A is nowhere near filling its Roche lobe. For now, the system is quiet. Both stars orbit in dignified silence, one burning, one cooling, separated by a gulf of space that mass cannot currently bridge. But the universe is patient, and stellar evolution is relentless. In roughly 600 million years, Sirius A will begin to leave the main sequence. Its hydrogen fuel will deplete in its core, helium will accumulate, the core will contract, the outer layers will expand. Sirius A will swell into a red giant, growing to many times its current radius. As it expands, its outer atmosphere will approach and eventually reach the Roche lobe boundary. Material will begin to stream across the gap between the two stars, flowing along a narrow channel from the surface of the giant to the gravitational well of the white dwarf. An accretion disk will form around Sirius B, a swirling vortex of stolen gas, heated to millions of degrees by friction and compression as it spirals inward. What happens then is uncertain and depends on the rate of mass transfer, the composition of the accreted material, and the specific physics of the accretion process. Slow accretion may lead to periodic nova eruptions that eject most of the accreted mass, preventing the white dwarf from growing toward the Chandrasekhar limit. Rapid accretion may lead to steady hydrogen burning on the surface, allowing the white dwarf to grow in mass more efficiently. The outcome, whether the system produces novae, a Type Ia supernova, or simply a common envelope event in which the white dwarf is engulfed by the red giant's atmosphere and spirals inward, depends on physical conditions that cannot be predicted with certainty this far in advance. The statistics of white dwarfs in the Milky Way are themselves worth contemplating. Our galaxy contains an estimated 10 billion white dwarfs, representing perhaps 5 to 10% of all stars in the galaxy. They are among the most common stellar remnants. Every star with an initial mass between roughly 0.5 and 8 solar masses, which encompasses the vast majority of all stars ever born, will end its life as a white dwarf. Only the most massive stars, those above about 8 solar masses, produce neutron stars or black holes. The white dwarf graveyard is vast, and its population grows with every passing century as more and more stars exhaust their fuel and join the ranks of the dead. Most of these white dwarfs are invisible to the casual observer. They are faint, small, and scattered throughout the galaxy's disk and halo. The nearest known white dwarf to Earth, aside from Sirius B, is Van Maanen's star, a solitary white dwarf about 14.1 light-years away in the constellation Pisces. It was discovered by Adriaan van Maanen in 1917, making it the first discovered solitary white dwarf. Van Maanen's star has a mass of about 0.67 solar masses and a surface temperature of around 6,100 Kelvin, making it much cooler and older than Sirius B. It is a relic of a star that died billions of years ago, slowly fading into the cosmic background. The nearest white dwarf to Earth is actually Sirius B itself, at 8.6 light-years. Its proximity makes it uniquely valuable for study, but also uniquely challenging because its proximity to the overwhelmingly bright Sirius A creates the glare problem that has bedeviled observers for over a century. The irony is precise and cruel. The nearest white dwarf is also one of the hardest to observe, because it happens to orbit one of the brightest stars in the sky. Beyond individual systems, the population of white dwarfs serves as a fossil record of star formation in the galaxy. Each white dwarf carries in its mass, temperature, and composition a record of when and how its progenitor star was born and died. By surveying the white dwarf population, astronomers can reconstruct the star formation history of the Milky Way, determine the age of different galactic components, and test theories of stellar evolution against a statistical sample of billions of objects. The Gaia spacecraft has been transformative in this regard, providing precise distances, luminosities, and motions for hundreds of thousands of white dwarfs across the galaxy. Every data release from Gaia adds new layers of detail to our understanding of the white dwarf population, and, through it, the history of our galaxy. The white dwarf luminosity function, a graph showing the number of white dwarfs at each luminosity, is one of the most powerful tools in galactic archaeology. Because white dwarfs cool at predictable rates, the luminosity function encodes the entire star formation history of the galaxy. A burst of star formation millions or billions of years ago would produce a cohort of white dwarfs that, today, would cluster at a particular luminosity, creating a bump in the luminosity function. A sustained period of steady star formation would produce a smooth distribution. A sudden cessation of star formation would produce a sharp cutoff at faint luminosities, because no new white dwarfs would have been produced recently, leaving a gap in the bright end of the distribution. Reading the white dwarf luminosity function is like reading the rings of a tree, each layer encoding a chapter in the history of its formation. The faintest, coolest white dwarfs are the oldest and thus the most valuable for determining the age of the galaxy. These objects are extraordinarily difficult to observe because they are dim, redshifted, and easily confused with other faint objects. But their detection, enabled by the combination of Gaia's precise astrometry and deep photometric surveys, has allowed astronomers to push the age estimate of the Milky Way's disk back to roughly 8 to 9 billion years, and the halo to 11 to 12 billion years. These ages are consistent with independent estimates from the ages of the oldest globular clusters and from cosmological models of structure formation, providing a reassuring cross-check between completely different methods. There is also the matter of white dwarf mergers and their contribution to the gravitational wave background. When two white dwarfs orbit each other in a tight binary, they lose energy through gravitational wave emission. The orbital period shrinks, the stars spiral closer. Eventually, they may merge. These systems are expected to be among the loudest sources of low-frequency gravitational waves, detectable by future space-based observatories like the Laser Interferometer Space Antenna, or LISA, which the European Space Agency plans to launch in the mid-2030s. LISA will be sensitive to gravitational waves with periods of seconds to hours, precisely the range produced by close white dwarf binaries. The galaxy is expected to contain millions of such systems, creating a foreground of gravitational wave noise that LISA will need to characterize and subtract before it can detect other sources. The white dwarf population, already important for electromagnetic astronomy, will become equally important for gravitational wave astronomy in the coming decades. The study of Sirius B, then, is not the study of an isolated curiosity. It is a window into a vast population of objects, a bridge between the physics of individual stars and the history of the entire galaxy, a connection between quantum mechanics and cosmology, between the exclusion principle and dark energy. This single white dwarf, invisible to the naked eye, orbiting a star you can see from any inhabited continent on Earth, carries within it threads that, if pulled, unravel into some of the deepest and most surprising stories in all of science. We have traced the story of Sirius B from its discovery as a gravitational perturbation, through its identification as a white dwarf, to its role as a standard bearer for quantum mechanics, general relativity, and observational astrophysics. But now we must go deeper, because what Sirius B truly reveals is not just a fact about one star. It reveals something about the nature of matter itself, about the relationship between permanence and impermanence, and about the strange trajectory that every complex structure in the universe must eventually follow. Consider what Sirius B is made of. Its core is carbon and oxygen, forged in the nuclear furnaces of its progenitor star. These are not exotic materials. Carbon is the basis of all life on Earth. Oxygen is the gas we breathe. The atoms in your body, the carbon in your muscles, the oxygen in your blood, were forged in the interiors of stars that lived and died before the sun was born. You are, quite literally, made of the same stuff as Sirius B. The difference is arrangement. In your body, carbon atoms are woven into intricate molecular chains, proteins and nucleic acids and lipids, organized into cells, organized into organs, organized into a conscious being reading these words. In Sirius B, those same carbon atoms are crushed into a degenerate lattice, stripped of their electrons, locked into a crystalline structure by pressures no terrestrial laboratory can reproduce. Same atoms, vastly different destinies. This is at its root a story about entropy. Entropy is the measure of disorder in a system, and the second law of thermodynamics states that entropy on average always increases. Stars are temporary violations of this trend. A star is an island of intense order in a universe trending toward diffuse chaos. It takes a vast cloud of gas and concentrates it into a dense, hot sphere. It takes simple hydrogen and fuses it into heavier, more complex elements. It radiates structured, organized light into a universe that would otherwise be filled with nothing but the faint, uniform glow of the cosmic microwave background. But the second law is patient. It always wins. The star burns its fuel, the fusion stops, the organized structure collapses, and what remains, a white dwarf, is a monument to the second law's inevitable triumph, but it is not a monument to total chaos. A white dwarf is not a formless cloud of dispersed energy. It is highly ordered in its own way, a crystal of carbon and oxygen held together by quantum mechanical forces, maintaining a definite mass, a definite radius, a definite temperature. It is ordered, but it is sterile. It generates no new energy. It supports no chemistry, no complexity, no life. It is order without creativity, structure without function, a perfect ruin. The philosopher might pause here and reflect on what it means that the universe produces objects like this. A white dwarf is the universe's way of saying that complexity is temporary, but structure is durable. The complex chemistry of a living star, the nuclear reactions, the convective currents, the magnetic fields, the stellar winds, all of this ceases when the fuel runs out, but the structure persists, the matter endures. The crystallized core will exist for longer than all the complex processes that created it combined. The building outlasts the builders by factors of thousands, but the building is empty, the lights are off, no one is home. This tension between complexity and persistence pervades all of physics. The most complex things in the universe, galaxies, stars, planets, organisms, civilizations, are also the most transient. They require constant input of energy to maintain their organization. Cut off the energy supply, and they decay. A galaxy without star formation becomes a collection of aging remnants. A star without fuel becomes a white dwarf, or worse. A planet without a star becomes a frozen, dark wanderer. An organism without food dies. A civilization without energy collapses. Complexity is expensive. It must be paid for continuously. and the currency is energy, flowing from concentrated reservoirs into diffuse sinks, from low entropy to high entropy, from order to disorder. Sirius B represents the aftermath of one such transaction. For 100 million years or so, its progenitor star converted gravitational potential energy and nuclear binding energy into light, heat, and heavy elements. That was the period of complexity, of activity, of creation. Then the fuel ran out. The star shed its outer layers. The core collapsed and the transaction closed. What remained was a white dwarf, a receipt for the energy that was spent, a permanent record of a temporary process. To appreciate the strangeness of this, consider a scaled comparison. Imagine compressing the entire history of Sirius B's progenitor star into a single human lifetime of 80 years. On this scale, the star forms from a collapsing gas cloud, ignites hydrogen fusion, and burns steadily on the main sequence for about 78 years. Then, in the final 2 years of its life, it swells into a red giant, sheds its outer layers, and collapses into a white dwarf. The entire dramatic death sequence, from the first signs of trouble to the formation of the remnant, occupies roughly the last 2.5% of the star's existence. Everything before that was steady, uneventful hydrogen burning. The spectacular death was brief, the quiet life was long, and the afterlife, the cooling white dwarf phase, stretches far beyond any human analogy. If the progenitor's lifetime was 80 years, the white dwarf's cooling phase would last roughly 80,000 years. The remnant endures 1,000 times longer than the star that created it. The ashes outlast the fire by an almost incomprehensible margin. This is not science fiction. This is the straightforward implication of well-established physics. The cooling timescale of a white dwarf is governed by its thermal energy content and its luminosity, both of which are determined by its mass, composition, and atmospheric properties. The calculations have been performed by generations of astrophysicists, refined with each improvement in our understanding of matter at extreme densities, and confirmed against the observed population of white dwarfs in the solar neighborhood. The patience of these objects is not poetic license. It is a quantitative, testable, and tested prediction of modern stellar physics. There is another way to appreciate what Sirius B represents in the cosmic economy. Think of the Sun. Every second, the Sun converts roughly 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons are converted into energy according to Einstein's equation. Energy equals mass times the speed of light squared. That energy radiates outward as sunlight, illuminating the solar system, warming the Earth, powering photosynthesis, driving the weather, and ultimately sustaining every living thing on this planet. 4 million tons per second every second for 4.6 billion years so far, with roughly 5 billion more years to go. The total energy output over the Sun's lifetime will be staggering. But it is finite. When the hydrogen is gone, the sunlight stops. And what remains is a white dwarf, a fraction of the Sun's original mass, containing a fraction of its original energy, slowly releasing that residual thermal energy into a universe that will be far colder and far emptier than it is today. Now consider the degenerate matter that comprises this object more carefully. In ordinary matter, atoms maintain their identities. An oxygen atom in your lungs is recognizably an oxygen atom. It has 8 protons, 8 neutrons, 8 electrons arranged in shells, a characteristic size of about 120 picometers. It participates in chemical bonds. It vibrates, rotates, interacts with its neighbors through electromagnetic forces. It has, in a meaningful sense, individuality. It behaves differently from a nitrogen atom, or a carbon atom, or a helium atom. In a white dwarf, individuality is crushed out of matter. The nuclei are stripped of their electrons. The electrons belong to no particular nucleus. They form a degenerate sea, a quantum fluid that belongs to the star as a whole, not to any individual atom. The nuclei sit in a lattice, their positions determined by the balance of electrostatic repulsion and the pressure of the surrounding electron sea. There are no molecules, there are no chemical bonds, there is no chemistry. The matter has been reduced to its most fundamental components, protons, neutrons, and electrons, and rearranged into a configuration that is as far from ordinary matter as anything in the visible universe. This is not destruction. The matter still exists. The carbon nuclei still have 6 protons each. The oxygen nuclei still have 8. but the organizational principles that govern ordinary matter, chemistry, molecular bonding, crystal structures in the conventional sense, have been superseded by a deeper and more fundamental set of rules. Quantum statistical mechanics governs this matter. The Pauli exclusion principle determines its structure. The distinction between bosons and fermions determines its fate. Sirius B is matter governed by the rules that underlie all of matter, but which are usually hidden beneath the more familiar rules of chemistry and thermodynamics. Strip away the superficial layers, compress matter to densities 1,000,000 times greater than anything on Earth, and you see the quantum mechanical substrate of reality laid bare. This is why physicists find white dwarfs so fascinating. They are natural laboratories for extreme physics. The conditions inside a white dwarf cannot be replicated in any terrestrial experiment. The highest pressures achieved in diamond anvil cells, the most powerful compression devices in any laboratory on Earth, reach perhaps a few hundred gigapascals. The pressure at the center of Sirius B is estimated at roughly 10 billion gigapascals. That is a factor of roughly 100 million beyond anything we can create on the ground. The physics of matter at these pressures, the equation of state of degenerate carbon-oxygen mixtures, the crystallization dynamics, the thermal conductivity of the lattice, all of these must be inferred from theoretical calculations and validated against astronomical observations rather than measured directly. There is another dimension to the physics of white dwarfs that deserves attention: their thermal evolution and what it tells us about time itself. A white dwarf is, thermodynamically speaking, a reservoir of thermal energy slowly leaking into space. The rate at which it leaks determines how quickly the white dwarf fades, and this rate depends on the thermal conductivity of the degenerate core and the opacity of the thin, non-degenerate atmosphere that blankets it. The core, composed of degenerate matter, conducts heat with extraordinary efficiency. Degenerate electrons are excellent thermal conductors because they can carry energy across vast distances without being scattered by the lattice of ions. The result is that the interior of a white dwarf is nearly isothermal, maintaining a uniform temperature throughout the core. All the interesting thermal physics happens in the thin atmospheric skin, where the transition from degenerate to non-degenerate matter creates an insulating blanket. It is this blanket, a layer perhaps a few hundred kilometers thick in a star 12,000 kilometers across, that controls the rate at which the white dwarf releases its stored heat. A thick, opaque atmosphere traps heat and slows the cooling. A thin, transparent atmosphere allows it to escape more rapidly. This means that the composition of a white dwarf's atmosphere has a direct impact on its cooling rate, and therefore on the age estimates derived from its temperature. A hydrogen atmosphere white dwarf like Sirius B cools differently from a helium atmosphere white dwarf, which cools differently from one with traces of heavier elements mixed in. The atmospheric composition acts as a valve, regulating the flow of thermal energy from the hot interior to the cold vacuum of space. Getting this valve physics right is essential for using white dwarfs as cosmic chronometers, and decades of theoretical work have been devoted to constructing detailed atmospheric models that account for the opacities of various chemical species under the extreme conditions of a white dwarf's surface. The magnetic fields of white dwarfs add yet another layer of complexity. Some white dwarfs possess extraordinarily powerful magnetic fields, reaching hundreds of millions or even billions of Gauss, compared to the Sun's average surface field of about 1 Gauss and the Earth's field of roughly half a Gauss. These magnetic white dwarfs, which comprise perhaps 10 to 20% of the known population, present theoretical puzzles. Where do such enormous fields come from? One possibility is that they are fossil fields, remnants of the magnetic fields of the progenitor star, amplified by the conservation of magnetic flux during the collapse from a giant star to a compact remnant. When a star with a radius of 100 million kilometers collapses to one with a radius of 6,000 kilometers, the magnetic field lines are compressed into a much smaller area, and the field strength increases by a factor proportional to the square of the radius ratio. A modest stellar field of a few hundred Gauss can become a white dwarf field of millions of Gauss through this mechanism alone. Another possibility is that strong fields are generated during the merger of two white dwarfs, a violent process that can amplify magnetic fields through dynamo action in the differentially rotating merger product. Sirius B itself has a relatively modest magnetic field, measured at less than a few thousand Gauss. It is not one of the dramatic high-field magnetic white dwarfs, but even this modest field carries information. Its weakness suggests that the progenitor star did not have an unusually strong field, and that Sirius B formed through a relatively standard evolutionary channel rather than through a merger or other exotic process. The magnetic field, or lack thereof, is another line of evidence in the forensic reconstruction of this star's history. Beyond magnetism, there is the question of rotation. White dwarfs, like all stellar remnants, are expected to rotate. The progenitor star rotated, and as its core contracted, angular momentum conservation should have spun it up, just as a figure skater spins faster when she pulls in her arms. Yet most observed white dwarfs rotate remarkably slowly, with periods of hours to days rather than the seconds or milliseconds that naive angular momentum conservation would predict. This suggests that significant angular momentum is lost during the red giant and planetary nebula phases, perhaps carried away by the expelled outer layers, or braked by magnetic coupling between the core and the envelope. The rotation rate of Sirius B has been difficult to measure precisely because of the observational challenges posed by its proximity to Sirius A, but it is believed to be a slow rotator, consistent with the general population. The interplay between cooling, crystallization, sedimentation, rotation, and magnetic fields makes each white dwarf a complex physical system, far richer than the simple, degenerate sphere that early models envisioned. Modern white dwarf physics is a thriving field that draws on quantum mechanics, statistical mechanics, plasma physics, solid-state physics, nuclear physics, and general relativity. A single white dwarf or a laboratory for all of these disciplines simultaneously, and the population of white dwarfs in the galaxy provides a statistical sample large enough to test theoretical predictions against observational reality with increasing precision. The Chandrasekhar limit, that critical mass of 1.4 solar masses, stands as one of the most profound boundaries in all of physics. Above this limit, the electrons cannot hold. Below it, they can. The limit is set by a handful of fundamental constants: the gravitational constant, Planck's constant, the speed of light, and the mass of the electron and the proton. These are not parameters that anyone chose. They are built into the fabric of reality. They determine the maximum mass of a white dwarf just as surely as they determine the charge of an electron or the speed of light. The Chandrasekhar limit is not an engineering constraint. It is a law of nature, as fundamental as the conservation of energy, as unavoidable as the increase of entropy. And Sirius B sits just below it. At 0.978 solar masses, it possesses roughly 70% of the maximum allowed mass. Its core is dense enough that the electrons are mildly relativistic, not fast enough to compromise the degeneracy pressure, but fast enough to remind us that this star lives in a regime where special relativity and quantum mechanics both matter simultaneously. It is not at the edge of the cliff, but it can see the edge. It is stable, secure, and patient, but it is not infinitely far from disaster. The fate of a white dwarf that exceeds the Chandrasekhar limit is different, depending on how the limit is crossed. If it crosses by slow accretion, the core heats gradually, carbon ignition occurs relatively gently at first, and the deflagration to detonation transition produces the classical Type ER supernova. If it crosses by sudden merger with another white dwarf, the dynamics are more violent, the geometry is more complex, and the resulting explosion may differ in its details. The diversity of Type E supernovae observed in nature, some brighter, some fainter, some with peculiar spectral features, may reflect this diversity of progenitor channels. The Chandrasekhar limit is a single number, but the ways of reaching it are many, and the consequences of crossing it are rich and varied. There is a philosophical weight to the Chandrasekhar limit that extends beyond astrophysics. It tells us that the universe has boundaries. There are things that matter cannot do, not because of engineering limitations or lack of resources, but because the fundamental laws of physics forbid them. An electron cannot share a quantum state with another electron. A white dwarf cannot exceed 1.4 solar masses and remain a white dwarf. A signal cannot travel faster than light. These are not obstacles to be overcome. They are the rules of the game. They define the space within which all physical processes must operate. They are the grammar of the universe, and no amount of effort or ingenuity can change them. The Sirius binary system will continue its stately dance for hundreds of millions of years to come. Sirius A will burn hydrogen in its core, slowly growing more luminous as it ages, following the well-established evolutionary track of a main sequence star of its mass. Sirius B will cool, imperceptibly slowly by human standards, its surface temperature declining by perhaps a few hundred degrees per billion years. The two stars will orbit each other, their gravitational embrace unchanging, their elliptical path traced and retraced every 50 years with clockwork precision. And far in the future, when Sirius A leaves the main sequence and swells into a red giant, the system will undergo a dramatic transformation. Mass may flow, novae may erupt, an accretion disk may blaze with X-ray light. The common envelope may swallow both stars. The outcome is uncertain, but it will be dramatic. The Sirius system, that familiar beacon of the winter sky, will become something strange and violent and new. Let that sink in. A star that human beings have used to navigate, to mark the seasons, to anchor their mythologies, will eventually become a site of stellar violence that would be visible from neighboring star systems. The steady, reliable dog star will transform into something unpredictable and dangerous. The sky our distant descendants see, if descendants there are, will be unrecognizably different from the one we know, and even that violence will eventually subside. After the mass transfer, after the nova eruptions, after whatever final fate awaits the system, there will be two remnants where once there were two stars, perhaps two white dwarfs, perhaps a white dwarf and a dispersed nebula, perhaps a single merged remnant. Whatever the outcome, the system will eventually settle into a new equilibrium, a new silence, a new patience measured in billions and trillions of years. The drama is always temporary. The silence is always permanent. Something is wrong with our assumptions about the universe if we think of stars as permanent fixtures and white dwarfs as anomalies. The truth is precisely reversed. The luminous, burning, fusion-powered stars that fill our sky are the anomalies. They are the brief, bright exceptions in a cosmos that is overwhelmingly dark, cold, and populated by remnants. The universe has been making white dwarfs for nearly as long as it has been making stars, and it will continue to make them long after the last star, capable of producing one, has exhausted its fuel. In the final accounting, when the last stellar fires have died, white dwarfs and their eventual successors, black dwarfs, will be the most numerous objects in the visible universe. They are not the exotic exceptions. They are the rule. They are what matter becomes when the universe is done with it. But for now, the system is quiet. Sirius A shines. Sirius B cools. The universe goes about its business. And we, fragile arrangements of the same carbon and oxygen that comprise that crystallizing remnant, have managed to figure out what it is, how it works, and why it matters. That is not a small accomplishment. It is, in its own way, as remarkable as the white dwarf itself. Everything we have learned about Sirius B applies, with minor adjustments, to our own sun. The sun is a main sequence star, burning hydrogen in its core, converting 4 million tons of matter into energy every second through the proton-proton chain reaction. It has been doing this for about 4.6 billion years and will continue for approximately another 5 billion years. But eventually, the hydrogen in its core will be exhausted. Helium ash will accumulate. The core will contract and heat. Hydrogen will begin to burn in a shell around the inert helium core. The outer layers will swell enormously. The sun will become a red giant, expanding to engulf the orbits of Mercury and Venus, and perhaps reaching as far as Earth's orbit. The details of Earth's fate during this phase remain somewhat uncertain. If the sun expands to encompass Earth's orbit, our planet will spiral inward through the sun's tenuous outer atmosphere, heated to thousands of degrees and eventually vaporized. If tidal interactions cause Earth's orbit to expand just enough to stay ahead of the advancing solar surface, the planet might survive as a scorched, irradiated husk, but survival is a generous word for what would be a world stripped of its oceans, its atmosphere, and every trace of the biosphere that once made it remarkable. Either way, the Earth as we know it will be gone long before the Sun reaches its maximum extent as a red giant. The oceans will begin to evaporate in roughly 1 billion years as the Sun's luminosity slowly increases, rendering the surface uninhabitable for complex life well before the dramatic red giant phase begins. After spending perhaps 1 billion years as a red giant, the Sun will shed its outer layers into planetary nebula, revealing its naked core. And that core, composed of carbon and oxygen forged during helium burning, will be a white dwarf, our white dwarf. It will have a mass of roughly 0.5 to 0.54 solar masses, about half the Sun's current mass, the rest having been expelled into the nebula. It will have a surface temperature of perhaps 100,000 Kelvin initially, hot enough to ionize the surrounding nebula and make it glow in brilliant greens and blues and reds. And it will begin to cool, slowly, steadily, inexorably, over timescales that make the entire current history of the universe seem brief. The cooling timescale of a white dwarf is set by its mass, its composition, and the opacity of its outer layers. Lower mass white dwarfs cool more slowly because they have less gravitational energy to release and smaller surface areas from which to radiate. The Sun's white dwarf, at roughly half a solar mass, will take approximately 15 to 20 billion years to cool to the point where it is no longer visible to the kind of telescopes we currently possess. Over far longer timescales, hundreds of billions to trillions of years, it will fade from white to yellow to orange to red to the faintest, dimmest red, and eventually, over timescales approaching 10 to the 15 years, 1 quadrillion years, it will become a black dwarf, a cold, dead, invisible sphere of crystallized carbon and oxygen emitting no light, producing no energy, interacting with the rest of the universe only through gravity. This is the Sun's fate. This is the fate of every star like the Sun, and it is a fate that connects the future of our solar system to the present of the Cis system. Sirius B has already become what the Sun will one day become. It is a preview, a forecast, a ghost of our future. When you look at Sirius in the night sky and imagine the faint white dwarf beside it, you are looking at the ultimate fate of the star that lights your days and warms your world. The timescales involved are worth contemplating, not because they are immediately relevant to human life, but because they reveal the true structure of cosmic time. A human life spans roughly 80 years. A civilization might last a few thousand years. The entire recorded history of humanity spans about 5,000 years. The Earth has existed for 4.5 billion years. The universe for 13.8 billion. But these numbers, immense as they seem, are small compared to the timescales of white dwarf cooling. A white dwarf will remain warm and detectable for tens of billions of years. It will remain physically intact for quadrillions of years. It will persist, in some form, for timescales that current physics cannot confidently predict, potentially until proton decay, if protons decay at all, dismantles it at timescales of 10 to the 37 or 10 to the 40 years. Let that sink in. An object that formed in a violent collapse, born from the death of a star, will persist for longer than every luminous star that will ever shine in the history of the cosmos combined. The lifetime of a white dwarf, measured against the era of starlight, is like the age of the ocean measured against the lifespan of a raindrop. We live in the raindrop. The white dwarf endures through the ocean. There is something humbling about contemplating these timescales alongside the brevity of human existence. If the entire future lifespan of a white dwarf were compressed into a single calendar year, the current age of the universe, all 13.8 billion years of it, would occupy less than the first second of January 1st. Human civilization, all of recorded history, would be an interval so brief that no clock could measure it. We are specks of time within a universe of time, transient sparks in a cosmos that measures its patience in quadrillions of years. And yet, these specks of time have managed to decode the physics of objects that will outlast them by factors that language struggles to express. The white dwarf future of our Sun carries another implication worth reflecting on. When the Sun dies and becomes a white dwarf, the elements it has forged during its lifetime, the helium in its core, The trace amounts of carbon and oxygen produced in its final burning stages will be locked inside the remnant, but the elements expelled in the planetary nebula, the outer layers of hydrogen and helium, enriched with traces of heavier elements dredged up from the interior, will be returned to the interstellar medium. They will mix with the gas and dust between the stars, enriching the raw material from which future generations of stars and planets will form. The Sun's death will contribute to the chemical evolution of the galaxy, adding its processed material to the great reservoir from which new worlds are born. Sirius B's progenitor did the same thing 120 million years ago. The cycle repeats, generation after generation, each stellar death enriching the cosmos with the products of nuclear synthesis. This cycle has consequences we can observe. The Sun is a relatively young star, formed about 4.6 billion years ago from material that had already been processed through multiple generations of stellar evolution. It contains roughly 2% heavy elements by mass, elements heavier than hydrogen and helium, forged in the interiors of stars that lived and died before the Sun existed. The oldest stars in the galaxy, formed in the first few hundred million years after the Big Bang, contain almost no heavy elements at all. They formed from nearly pristine hydrogen and helium, the primordial elements produced in the first few minutes of the universe's existence. The difference between these ancient metal-poor stars and younger, metal-rich stars like the Sun is a direct consequence of the nucleosynthetic cycle, the steady accumulation of heavy elements through billions of years of stellar births and deaths. In the very far future, the universe will be populated almost exclusively by black dwarfs, neutron stars, and black holes. The era of luminous stars will have ended. The last red dwarfs, the smallest and most miserly stars, will sputter out in perhaps 10 to 20 trillion years. After that, no new light will be generated by nuclear fusion anywhere in the universe. The cosmos will enter what physicist Fred Adams has called the degenerate era, a period lasting from roughly 10 to the 15 to 10 to the 37 years, during which the dominant objects in the universe are degenerate stellar remnants, slowly cooling and occasionally interacting through rare gravitational encounters. In this era, white dwarfs and black dwarfs will be the most common macroscopic objects in existence. They will outnumber everything else. They will be the universe's primary inhabitants, and they will reign in darkness for timescales that dwarf the current age of the cosmos by factors of millions and billions. This is not a depressing vision. It is simply the universe as it is, governed by the laws of thermodynamics and the fundamental constants of physics. The second law guarantees that organized energy will dissipate. Stars are temporary engines that convert gravitational and nuclear energy into light. White dwarfs are the ashes of those engines, cooling toward equilibrium with the cosmic microwave background. The story of the universe is, in its broadest strokes, the story of a transition from hot, dense, uniform energy to cold, sparse, structured matter, and eventually to cold, sparse, inert matter. Sirius B is one chapter in that long transition, a waypoint on the road from the Big Bang to the heat death of the cosmos. Yet there is something deeply clarifying about understanding our cosmic context, knowing that the stars are not eternal, that even the most brilliant luminaries will one day exhaust their fuel and fade, reframes the human relationship with the sky. For most of human history, the stars were symbols of permanence. Civilizations rose and fell, empires conquered and crumbled, individual lives flickered like candle flames, but the stars endured. Sirius burned in the Egyptian sky 5,000 years ago, and it burns tonight. That apparent permanence was a comfort, a fixed point in a turning world. But the permanence is an illusion. Sirius A will die. It will swell, shed its layers, and collapse into a white dwarf. The brightest star in the sky will become two fading embers, orbiting each other in silence, cooling into the dark. The fixed point was never fixed. It was merely slow, and this brings us to a strange and profound realization. If the universe is temporary, if the stars are temporary, if the planets and the chemistry and the conditions for life are all temporary, then consciousness is the most perishable commodity in the cosmos. The window during which the universe can know itself is vanishingly small compared to the vast stretches of time during which it will exist in cold, inert, unconscious silence. The era of awareness, The brief flicker during which matter organizes itself into brains that ask questions about white dwarfs is a tiny parenthetical in a story written almost entirely in the language of thermodynamic equilibrium. This does not make the parenthetical meaningless. It makes it everything. All of art, all of science, all of love and curiosity and discovery exists within this parenthetical. Every question ever asked, every answer ever found, every moment of understanding that has ever passed between one mind and another, or between a mind and the cosmos, occurs in this narrow window when the universe happens to be warm enough and complex enough to sustain the astonishing process of thought. When the window closes, there will be no one left to mourn it. The white dwarfs will not grieve. The black holes will not remember. The cooling remnants of dead stars will drift through an expanding void without any awareness that awareness ever existed. But here is the counterpoint, and it is important. We are here. We exist in the narrow window of cosmic time when stars shine, when chemistry is possible, when carbon atoms can arrange themselves into molecules that think and wonder and ask questions about white dwarfs 8.6 light-years away. The fact that this window is finite, that it will eventually close, does not diminish it. If anything, it makes it more precious. The universe will be dark for far longer than it will be lit. The era of complexity, of life, of consciousness, occupies a sliver of cosmic time so thin it is almost invisible on a logarithmic chart of the universe's history. That we happen to exist within that sliver, that we have developed the tools and the curiosity to understand objects like Sirius B, is a circumstance of extraordinary improbability and extraordinary value. Every heavy element in your body was forged in a star. Every atom of carbon, every atom of oxygen, every atom of iron and calcium and phosphorus was assembled in the nuclear furnaces of stars that lived and died before the sun was born. Some of those atoms may have been released in the very kind of supernova that white dwarfs produce. The calcium in your bones may have been synthesized in the thermonuclear detonation of a white dwarf that exceeded the Chandrasekhar limit 4 or 5 or 6 billion years ago, in a galaxy far enough away that the light of the explosion reached Earth's raw materials before the solar system formed. The carbon in your DNA may have been ejected in the planetary nebula of a star not unlike the progenitor of Sirius B, drifting through interstellar space for millions of years before being swept up in the collapsing cloud that became our Sun. This is the nucleosynthetic cycle, the great loop that connects stellar evolution to the chemistry of life. Stars forge elements. Stars die and scatter those elements into space. New stars and planets form from the enriched material. On at least one of those planets, the elements assembled themselves into organisms that eventually built telescopes and pointed them at the sky. The cycle runs on stellar death, without stars dying, without planetary nebulae dispersing their contents, without supernovae seeding space with heavy elements. The raw materials for rocky planets and living organisms would not exist. Life owes its existence to the death of stars. You owe your existence to objects like Sirius B, or rather, to the predecessors of objects like Sirius B, stars that died and donated their processed material to the interstellar medium before the sun was born. The scale of this cycle is worth one more moment of reflection. The Milky Way galaxy contains roughly 200 to 400 billion stars. Of these, the vast majority are low-mass stars that will eventually become white dwarfs. The galaxy has been forming stars for roughly 13 billion years, and during that time, billions of stars have already completed their life cycles, died, and become white dwarfs. Each death scattered processed material into the galaxy. Each death enriched the reservoir from which future stars and planets formed. The Sun, our Sun, is a relatively recent product of this enrichment. It formed from a cloud of gas and dust that had already been cycled through at least one and possibly several generations of stellar nucleosynthesis. The iron in the Earth's core, the silicon in its mantle, the carbon and nitrogen and oxygen in its atmosphere and its life, all of these elements were donated by stars that died before the solar system existed. We are, in the most literal sense, the children of stellar death, and white dwarfs, those quiet, cooling remnants scattered throughout the galaxy, are the tombstones that mark the graves of our ancestors. If you could somehow gather all the white dwarfs in the Milky Way into one place, you would have roughly 10 billion objects, each about the size of Earth, but with masses comparable to the Sun. Their combined mass would represent roughly 5 to 10% of the galaxy's total stellar mass. These silent remnants collectively hold a substantial fraction of the galaxy's processed matter, locked away in degenerate carbon-oxygen cores that will persist for timescales far longer than the galaxy itself will remain gravitationally bound. The white dwarf population is not merely a curiosity or a footnote in the story of the galaxy. It is a major, essential character, a repository of mass, a record of history, and a glimpse of the future that awaits nearly every star in the sky. This is why a white dwarf is never just a dead star. It is a node in a network of creation and destruction that spans the entire galaxy and the entire history of the universe. It is a record of nuclear processes, a contributor to chemical enrichment, a potential source of future explosions, and a laboratory for physics at extremes no human technology can reproduce. It is small and faint and easy to overlook, but its significance is vast. Its connections are deep. Its story is the story of the universe told through the lens of a single object. Go outside tonight. If you live in the northern hemisphere and the season is right, look south in the winter sky and find the constellation Orion. Follow the 3 belt stars downward and to the left. The first bright star you reach, blazing with a blue-white intensity that outshines everything in its neighborhood, is Sirius, Alpha Canis Majoris, the dog star, the brightest star in the night sky, and one of the most observed objects in the history of human civilization. Now imagine what you cannot see. Right beside Sirius, separated by a few arc-seconds that your eye cannot resolve, orbits a companion. It is small, roughly the size of Earth. It is dense, a teaspoon of its material weighing as much as 5.5 tons. It is hot, about 25,000 degrees at its surface, far hotter than the Sun, and it is dead. No nuclear reactions burn within it. No energy is being generated. It is a remnant, a ruin, a crystallizing sphere of carbon and oxygen held up by the quantum mechanical stubbornness of electrons that refuse to share the same quantum state. You cannot see it. Not with your eyes, not with binoculars, not with most backyard telescopes. It is lost in the glare of its brilliant companion, a faint spark beside a searchlight. But it is there, and its existence changed the course of physics. It was predicted before it was seen, a ghost inferred from the wobble of its companion. Its discovery confirmed that gravity could reveal what light could not. Its spectrum revealed a paradox, a surface too hot for its feeble luminosity, a contradiction resolved only by accepting that stars could be as small as planets. Its density shattered classical physics and demanded a new explanation rooted in quantum mechanics, in the Pauli exclusion principle, in the strange behavior of fermions under extreme compression. Its gravitational redshift confirmed Einstein's general relativity. Its mass, so close to the Chandrasekhar limit, connects it to the most violent explosions in the cosmos, the Type Ia supernovae that revealed the accelerating expansion of the universe and the existence of dark energy. Its cooling rate helps astronomers measure the age of the galaxy. Its crystallizing core tells us that the universe is filled with planet-sized diamonds drifting through the void. Its presence in a binary system raises the possibility of future mass transfer, nova eruptions, and perhaps, in the unimaginably distant future, a thermonuclear detonation that would outshine 100 billion stars. All of this from a single faint point of light that you cannot even see. This is the nature of the universe. The most profound truths are often invisible. The most important objects are often the most unassuming. The forces that shape the cosmos, gravity, quantum mechanics, thermodynamics, operate without spectacle, without drama, without any regard for human attention. The universe does not label its important objects with bright colors and flashing signs. It hides neutron stars in the static of radio telescopes. It conceals black holes behind veils of warped spacetime. It tucks white dwarfs beside brilliant companions where only the most careful observations can tease them out. Consider the chain of discoveries that led us here. In 1844, a mathematician noticed that a bright star was wobbling. In 1862, a telescope maker saw a faint spark in the glare. In 1915, an astronomer measured an impossible spectrum. In 1926, a physicist explained how electrons under extreme pressure could hold up a star. In 1930, A young man on a steamship calculated the maximum mass of a dead star and discovered a limit written into the fabric of reality itself. In 1995, an orbiting telescope measured the warping of spacetime around a distant object and confirmed that Einstein's equations described the universe exactly. In 1998, exploding white dwarfs revealed that the universe was accelerating into the void, driven by a force no one had predicted and no one yet understands. Each discovery built upon the last. Each answer opened a deeper question. Each generation of scientists stood on the shoulders of its predecessors, seeing farther not because they were taller, but because the mountain of accumulated knowledge grew higher beneath their feet. Sirius B does not care that you are thinking about it. It does not know that it exists. It is a ball of degenerate matter, cooling in the dark, following the laws of physics with absolute fidelity and absolute indifference. It will continue to cool for billions of years, after the last human being has lived and died. It will persist in some form for trillions of years after the sun has joined it in the white dwarf graveyard. It will endure long after the Milky Way has merged with Andromeda and the combined galaxy has ejected most of its stars into intergalactic space. It is permanent in a way that no living thing, no civilization, no planet, and no star can match, and yet we figured it out. We decoded its wobble. We unraveled its spectrum. We invented the physics to explain its density. We measured its gravitational redshift. We used its kin to discover that the universe is accelerating into oblivion. From our fragile position on a tiny planet orbiting an ordinary star in an unremarkable corner of an average galaxy, we reached out with mathematics and telescopes and imagination and decoded the nature of an object so extreme that the physics required to describe it did not exist when it was discovered. That is the real story of Sirius B. Not just the physics, not just the history, not just the numbers. The real story is the extraordinary capacity of the human mind to understand the universe in which it finds itself, to look at a wobbling star and deduce the existence of an invisible companion, to look at a faint spark of light and measure the curvature of space-time around it, to understand the quantum mechanical behavior of electrons in a regime so far removed from ordinary experience that it might as well be another universe entirely. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. The white dwarf reminds us of this. It was once a star, blazing with the light of 5 suns, dominant in its binary system, the brighter of the two companions. Now it is a fading ember, smaller than the planet we stand on, outlived by its lesser companion. The mighty fell, the modest endured, and the remnant persists in a state that neither the living star nor the living observers who study it can truly experience. Degenerate matter exists at conditions so extreme that human intuition fails entirely. We can describe it with equations, we can measure its properties from afar, but we cannot touch it, hold it, or feel what it is like to be matter compressed to 1,000,000 grams per cubic centimeter, held up by the collective defiance of electrons against the laws of classical physics. The ancient Egyptians watched Sirius rise before dawn and used its appearance to predict the flooding of the Nile. They called it Sopdet and associated it with the goddess Isis. They built temples aligned to its rising. For them, Sirius was a herald of abundance, a bringer of life-giving waters, a celestial calendar marking the rhythm of the agricultural year. They could not have imagined that the star they venerated had a companion, a dead star the size of the Earth, with the mass of the Sun, held together by a principle of physics that would not be discovered for 5,000 years. The universe they looked at was the same universe we look at now, but the depth of what we see has changed beyond all recognition. We are made of the same elements as that white dwarf, carbon and oxygen, forged in stellar cores, scattered by stellar deaths, gathered by gravity into a planet where, for a brief and remarkable moment in cosmic time, matter became aware of itself. We are the universe examining itself, and when we study Sirius B, we are studying our own origin, our own future, and our own nature. The star is out there right now, at this very moment, 8.6 light-years away, a sphere of crystallizing carbon and oxygen, 12,000 kilometers across, 25,000 degrees at its surface, slowly cooling in the shadow of its brighter companion. It has been cooling for 120 million years. It will cool for 100 trillion more. It asks nothing of us. It needs nothing from us. It does not require our attention or our understanding to continue its slow, patient fade into darkness. But we gave it our attention anyway. We noticed the wobble, followed the clue, measured the paradox, invented the physics, and mapped the space-time around a star we can barely see. And in doing so, we discovered something about the universe and about ourselves. We discovered that the cosmos is stranger than anyone imagined. That matter can exist in states that defy common sense. That the death of a star can illuminate the fate of the universe, and that a small, faint, invisible companion to the brightest star in the sky can carry within it some of the most profound truths that science has ever uncovered. The white dwarf will outlast us all, but for now, we are the ones who understand what it is. And that, for the brief moment we are here, is enough.